everyone, my name is Benjamin Bergner, and in this video I want to present token Cropr, which is a token pruning method for vision transformers. And this is a joint work with Christoph Lippert and Aravind Mahendran. As you know, AI is now applied in many real-world applications, for example in autonomous driving or in robotics. And many of these real-world applications require a low latency and high throughput. For example, in autonomous driving, we might have multiple cameras that process or that have to process multiple images in parallel, for which high throughput is needed. Or if you think about edge devices like smartphones, AI solutions need to be very energy efficient in order to not to drain the battery too much. And this is in contrast to vision transformers, which exhibit quite a lot of inefficiencies. In particular, vision transformers use self-attention layers, which scale quadratically in the sequence length. And nowadays we have many high-resolution images, and each patch in those images is represented by a single token. And the number of tokens remains unchanged throughout the network. And this is different to convolutional neural networks, for example, which apply pooling to reduce the representation size if we go deeper into the network. And here we want to achieve something similar to max pooling in particular, where irrelevant tokens are pruned out. But the pruning decision is based on task relevance and not based on heuristics. So the overall goal of this work is to improve inference efficiency, in particular throughput, while maintaining high task performance. So how does this work? Token Cropr starts with an image as input here in the bottom left, and the patches are then embedded. So we get for every patch a single token. And then in a standard vision transformer, you would apply a vision transformer block one after the next. And then in the very end, we have a head, for example, a classification head. Now in this work, we add Cropr modules on top of every vision transformer block to prune out the least relevant tokens. So we start with a few tokens here, for example, the background sky, which is not important to classify that this image shows a castle. And then later on we prune more tokens also from the lake down here. So we prune more and more tokens throughout the network. The prune tokens, however, they are not thrown away for good, but they are reintroduced just before the final vision transformer block, where they are then concatenated with the salient tokens. And this is what we call last layer fusion, because the last vision transformer block has then the goal of aligning these representations. So in this way, we are not throwing away any information, we are just prioritizing salient information. And the pruning process can be illustrated by a pruning map, where brighter tokens are retained in later layers of the network. And the module is called Cropr because it stands for cross-attention pruning. And by using Cropr, we observe an acceleration of vision transformers by 1.5 to 4x. And we apply it to multiple different tasks like classification, semantic segmentation, object detection, and instance segmentation. But before we go into the experiments, I want to spend a few more minutes on the Cropr module itself. So how does the module look like? And during training, we have our input tokens down here, and those go into a scorer. And the scorer introduces learnable query tokens. And then we compute an attention matrix, capital A, followed by an aggregation operation. So we basically sum across the learnable queries to obtain an attention vector, which has a single score for every input token. And then we simply choose the top k tokens according to the attention scores and forward those top k tokens to the next layer. And the remaining tokens, they are pruned out. But how are the queries learned here? This happens through the cross-attention aggregator and intermediate heads. So the attention matrix then goes into the cross-attention aggregator together with the input tokens, which represent the values. And then we get a summary representation for the input tokens, which is then input to an intermediate head, which is then learned together with the learnable queries. Importantly, we also add a stop gradient operator in order to avoid gradient interference with the main task head. During inference, we can introduce multiple optimizations. For example, the cross-attention aggregator and the intermediate head of every Cropr module is not needed anymore, so we can simply remove them. The second optimization is that we can observe that the attention matrix is not used anymore. The attention matrix was primarily used by the cross-attention aggregator in order to compute the summary representations. But since this is not used or needed anymore, we can simplify this whole operation by aggregating the learnable queries into a single query vector. And then we can compute a vector matrix multiplication to obtain the attention scores directly, which then goes into the top k operator. And by doing this optimization, we get a throughput that is similar to random pruning and much faster than the non-optimized Cropr, and also much faster than the no pruning baseline, obviously. We apply Cropr to image classification on ImageNet, and we compare it to the no pruning baseline and to various other token pruning baselines and token pruning methods and token merging methods. The rightmost column indicates the throughput gain compared to the no pruning baseline. And if we look at this first section here, where we apply last layer fusion to each method, then we see that Cropr performs very favorably compared to these baselines with comparable throughput. If we look at the second section, where LLF is not applied, then we see that Cropr also performs very well compared to these other methods, while having the highest throughput gain. We also noted that with a constant pruning schedule indicated by this arrow, that some methods they don't work well with this pruning schedule. So we introduce a second pruning schedule, which is applied in 3 stages instead of every layer. Here the total pruning rate is a bit lower than in the constant schedule, which is reflected in the overall lower throughput. And also here in this case, we perform better than other pruning methods and other merging methods while having similar throughput. We also apply Cropr to a state-of-the-art EVA 2 model, and here we get a throughput improvement of 2x, but here the performance drop is only 0.2 points. So this is a very good results in our opinion. Cropr is also applied in a more aggressive manner, where 80% of all tokens are removed after the third transformer block, and only after that block. And here the throughput gain is 4x at the moderate performance drop of 1.1 accuracy points. We also apply Cropr to different model capacities, to bit base, large and huge, as well as different image resolutions. And here we can observe that the throughput gain increases with larger models and with larger images, but the performance drop decreases. Yeah? For example, in ViT base, we have a performance drop of 0.9 accuracy points, and in ViT huge, the performance drop is reduced to 0.4, but the throughput gain is increased in the huge model. And for image resolutions, we see that with larger images, the performance drop becomes marginal, but the throughput gain is significant at 2.1x. We also apply Cropr to semantic segmentation, where again we compare it to the no pruning baseline, and here we see that it performs very similar to the no pruning baseline with a 2x throughput improvement. And here on the right side, we also show pruning maps, the predictions of Cropr and the ground truth label. And here we see that Cropr prunes primarily tokens from staff classes earlier. For example, the floor down here, or the sky, which can be considered background. And here also the floor and the wall. Interestingly, the predictions remain consistent, even though the tokens are pruned out very early. And we hypothesize that LLF helps to align the representations of pruned tokens and the salient tokens that are kept. Interestingly, also some patches or tokens are retained that can be considered background. And this is likely due to the fact that in semantic segmentation, all the information is important, because we want to segment the whole image. And if you remember, the pruned tokens, they are not thrown away, but they are reintroduced just before the last vision transformer block in an operation called last layer fusion. An alternative to last layer fusion would be to concatenate the pruned tokens after the last vision transformer block, right before the head. If we would do this and we look at the representations of every layer, then we can see that there are clear clusters forming for every layer. Instead, if we use last layer fusion, then we have more uniform representations, which suggest better synchronization between the tokens. And we hypothesize also that the final head, it's easier for the final head to make the final prediction for every token if they are more uniformly represented. And this is also reflected in the results, where the token concatenation baseline performs much worse than last layer fusion. Furthermore, last layer fusion does not introduce additional parameters, so it simply concatenates the tokens before the last vision transformer block. So it's a pretty straightforward method that is not special to Cropr. You can also apply it to your favorite token pruning method. And we also compared to some other baselines. Here, please refer to the paper to see the details. Finally, Cropr is also applied to object detection and instance segmentation on the COCO dataset. And here we see a throughput improvement up to 2.4 x at the moderate performance drop. Importantly, here we prune 97% of all the tokens, so quite a lot of tokens are pruned. And if we observe the pruning maps here, we see that Cropr focuses on the most important objects, like the clock here, the cars down here, and also the passengers of this bus. and even the imaginary passengers of this car, which is quite interesting. Furthermore, if we look at some more images, we see that Cropr retains tokens at the boundary of the objects, which is quite intuitive for object detection and instant segmentation, because if you know the class of the boundary of an object, then you can simply fill in the remaining parts. We also did some ablations for the Cropr architecture. For example, we compared a multi-head attention style with a simpler style where only a single head is used in the cross-attention layer, and no projection layers are used for the queries, keys, and values. And it turns out that this performs more or less similar to multi-head self-attention, but is much faster. So multi-head self-attention is not needed in this setting. Furthermore, we tried using an MLP within the cross-attention block versus not having the MLP, and it turns out that the performance is better with the added capacity, but the throughput and the flops remain the same, simply because during inference we can remove the cross-attention aggregator and the auxiliary head. Furthermore, we looked at using top K in the router compared to sampling, and top K performs better than sampling from the attention distribution. And finally, we also tried to not use a stop gradient operator here, but yeah, this performs worse than adding stop gradient operators, and this is likely due to avoiding gradient interference between the main task loss and all the intermediate losses. And finally, we also did some ablations for throughput. Here in this case, we compare FP32 automatic mix precision and automatic mix precision with flash attention for multiple image resolutions. And here we see that we get up to 8.9x throughput improvement for large images and automatic mix precision. And when using flash attention, the throughput gain is generally decreased, but it's still significant for larger images. And the total pruning rate remains constant across the different image sizes. And here's another interesting finding which we observed. So M is the number of remaining tokens after pruning, and it turns out if M is divisible by 8, we get higher throughput improvements compared to the no pruning baseline. And we observed that if we reduce the number of retained tokens by 1, such that the number of remaining tokens is not divisible by 8 anymore, then we get less throughput improvement. And especially for larger images, this difference is quite substantial. So if you ensure that the number of remaining tokens is always divisible by 8, you get more throughput improvement. And you can see and read more details about this experiment in the appendix. Last but not least, I want to thank my supervisor, Christoph Lippert, and also Aravind Mahendran for the mentorship and the ongoing feedback and collaboration in this project. And yeah, here are also some QR codes. Please check out our paper and code base on GitHub. Thanks a lot.